This is a recording for the Section 9.3 Reading Guide, Tests About a Population Mean. You can read through the section summary and the learning targets and define the vocabulary and concepts on your own. They also go through the four-step process for state, plan, do, and conclude. So it's a good summary to look back on with the formula and everything else. But we're going to look at the check for understanding, the first concept. Problem says that humerus bones from the same species of animal tend to have approximately the same length to width ratios. When fossils of humerus bones are discovered, archaeologists can often determine the species of the animal by examining these ratios. It is known that the species Molichius primatium exhibits a mean ratio of 8.9. Suppose 41 fossils of humerus bones are unearthed at a site on Minnesota's Iron Range, where the species was known to have lived. Researchers are willing to view these as a random sample of all such humerus bones. The length to width ratios were calculated and are listed below. Test whether the population mean for the species that left these bones differs from 8.9 at an alpha 0.05. So, we have all of our data. And they told us that there were 41. We also have the mean ratio, and they even gave us the symbol that its mu is 8.9. Our first step in conducting this test, which they want us to calculate at alpha equal to 0.05, compare our p-value to. And we want to know if it differs from 8.9. So that's going to be that not equal to. First thing whenever we do a test is that we need to do our four-step process. So that's the state, plan, do, conclude. So for the state part, I'm going to look at my symbol, which is mu, and I'm trying to determine the mean ratio of the species Molichius primatium for humerus bones is 8.9. And since we wrote that out in context, we can now just write that our HO is mu equals 8.9, and the HA is that mu is different than 8.9. Then the plan part, first one for all these tests and intervals is that we have a random sample. They told us we had a random sample. So we have a random sample of 41 fossils. Now they gave us all the data. So normally I would go ahead and put it in my list, which I've already done, and stat enter, got them all in there, all 41 of them. And then I turned on my stat plot for a histogram, and I zoom 9, and I see that it's roughly symmetric and unimodal. I could take the time to continue on and copy this down on my paper. However, we have 41 in our sample. And 41 is greater than 30. So I'm just going to add on to the one sentence I already have. We have a random sample of 41 fossils, comma, which is larger than 30. And that's good enough. So I can continue and say with conditions met, we can apply the t-distribution and do a t-test. So the test I should say do a t-test for one sample mean. Now, I'm glad that I already put the data in because I do need the data for the actual test part. So I'm going to hit Stat, go over to Test, do a t-test. I have data. I put in an L1. My mean is supposed to be 8.9, and they said if it differs, so that's not equal to. Calculate, and I get my t-score, my p-value, x-bar, s sub x. I'm going to go ahead and record all that down. So the test statistic, the t-score, is 1.97. Our p-value is 0.056, which technically could be rounded to 0.06. We have x-bar is 9.269. The standard deviation of our statistic is 1.199. Our sample size is also 41. Now we write our conclusion. With a p-value larger than 0.05, alpha equal to 0.05, because it's 0.056. I know that's close. Yes, you could always change your alpha level, but if we stick with it, because they told us to use 0.05, and it is larger than 0.05, we fail to reject the HO. We do not have evidence that the mean ratio in the fossil bones differs from 8.9. Okay, so that wraps up. They didn't ask us to interpret a p-value, so we don't need to. That's the first check for understanding. The second one takes us into a matched pairs test. Now in class we did the chubby bunny, which is what's happening next door right now in Ms. Hankins' room. If you hear background laughter, that's what that is. However, this is something that's more realistic, because out in the real world you're not going to go asking people how many marshmallows they can stuff in their mouth and how many they actually do. So we have a study measured how fast subjects could repeatedly push a button when under the effects of caffeine. Subjects were asked to push a button as many times as possible in 2 minutes after consuming a typical amount of caffeine. During another test session, they were asked to push the button after taking a placebo. The subjects did not know which treatment they were administered each day, and the order of the treatments was randomly assigned. The data given in presses per 2 minutes for each treatment follows. Use a paired T procedure to determine whether or not caffeine results in a higher rate of beats on average per 2 minute period. So, we have our subject numbers, we have beats with the caffeine and with the placebo. We're trying to see if they're different. So we're going to look over here in this column at their differences. Now I know that you are all in AP statistics, so you can subtract, but remember there are times that we just need to speed things along, and sometimes you tend to type things in wrong or you just think too fast for your brain. So I'm going to go ahead and put all my caffeine in L1. And this is good to know if they give you ever a longer list or if you have decimals. I'm just putting them all in L1. And then in L2, I'm going to put the placebo. Oh my goodness, I never put him over. I'm sure if we were in class right now, somebody would have been yelling at me, Ms. Blowjack, what are you doing? Okay, try that again. Okay, now I'm going to let the calculator subtract for me. You don't have to do it this way, but it's one way. You go up, you highlight your L3, hit enter. The question is, which way do you want to subtract? It doesn't really matter which way you want to subtract. It's asking if there's a higher rate of beats per minute with the caffeine. So if we do caffeine minus the placebo, that would give us a positive amount if we're assuming that caffeine is higher. So we would be looking for things that are higher than 0. So as I'm thinking about this, I could write my parameter out. So my state, I have the mean difference, mu sub d is the mean difference. Or some of you might like writing it as the average of the differences. Because that's really what we're looking at. For beats, how did they define it quickly? In beats per 2 minutes of subjects with caffeine minus subjects with placebo. Then the null would be mu sub d equals 0, that there's no difference. And the alternative is we're trying to see if there's more beats per the 2-minute period when the subjects had caffeine in their system. So it should be greater than 0. Now that I've got that figured out, I'm going to go back and look at my L3, and I want to do L1, the caffeine, minus L2, the placebo. So I'm going to do L1 minus L2, and it gives them to me. So I can just copy down that list on my paper so that everyone looking at my paper can tell what I did. And I can even write up here beats caffeine minus placebo and write the difference right here. I'm thinking in my head, I wonder if I'm going to have outliers because I see some pretty low values and some pretty high ones. Now that I have them all on my list, I can carry on and do the plan. Were the subjects randomly chosen? They did not know which treatment they were administered each day. and the order of the treatments was randomly assigned. Well, the subjects were not randomly chosen. So I'm going to say subjects were not randomly selected, but the treatment was randomly assigned. And if I think I need more with that, I can also say that 11 subjects is less than 10% of all possible subjects. So that's a lot for just the first condition, but now I feel a little safer in what I'm writing. Now since there are only 11, I've got to see how skewed my data are. So I'm going to go to my L3, and I'm going to do, I'll start with the histogram. I know some of you like box plots. Let's actually start with the box plot. Since there's less than 15, I want to make sure there's no outliers. And I'm going to zoom 9. Oops, changed my list, L3. Zoom 9. And there are outliers. Gee. But there's outliers on both sides. Let me look at the histogram and see how symmetric I could possibly make it look, because the rest of this problem doesn't say anything about not choosing to do this problem. I could write proceed with caution if I'm not feeling safe about it. If I look at my window, let's change that to -60 and go up to 200, and we can count by, try to count by tens maybe. See what happens. 8 point, we could change that to 10 and count by ones, graph. Still looks a little skewed. If I make my scale bigger, maybe it'll make things better. So let's change it from -100 to 200 and count by 50. Does that make anything better? Hit graph. Wow, yeah, of course it does. Oh, it looks pretty symmetric now. Aren't statistics wonderful? I'm going to copy that down, and just in case you need to see the window again. There it is. You can hit the pause button, put it in your calculator. Looking at my graph, that axis, the y-axis, is in there, remember, because 0 is supposed to be in the middle. And when I hit trace, I'm just writing down the lowest value here is -100, and I went up to 200, and I've got 1, 1, 5, 3, 1. Pretty symmetric. So data, or what's our data? The differences in beats per 2 minutes are unimodal and roughly symmetric. So with that mention, we can proceed with conditions met. We can apply t-distribution and do a t-test for the difference in means. for the difference of one sample mean? I think that would be okay. Trying to think of a quick way to write it. Now the do. I'm just going to go to my calculator once again, hit stat, go over to test, and do a t-test of the differences. I have data. I'm hoping that it's 0, or it's supposed to be 0. I have my data in L3, and I'm looking to see if it's more than. Now if you had subtracted in the other direction, you would select the less than. Calculate. They gave us a t-score, p-value, x-bar, everything we need. So I'm just going to copy that down onto my paper. T-score is 1.373. My p-value is 0.0999. And my x-bar is 20.182. And the S sub x, the standard deviation of the statistic, is 48.748. Now I'm going to come over here and write my conclude, trying to fit it all in, which I have plenty of room. With a p-value, it's higher than 0.05, of 0.0999, which is greater than alpha equal to 0.05, we fail to reject the HO. We do not have evidence that the average of the differences for beats per minute, beats per 2 minutes of subjects with caffeine minus subjects with placebo is greater than 0. I know that's super wordy, but I put it in context and I basically rewrote what I had written up here with the parameter, and I just put in greater than 0 instead of equal to 0. Okay, that wraps up that problem.